Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I will be going over how to find the pH of a weak acid solution. So in this case what we're going to be doing is the same thing. You want to set up your ice chart, you want to have a balanced equation, and then use that ice chart and the equation to find the equilibrium expressions for your for the things you're looking for to plug into your Ka expression, and then once you find your X value, then you can find the concentration of your hydronium ion, and then from there you can find the pH using the negative log. So in this example, we'll say we're going to be finding this should say, oops, we're going to find the pH. So finding the pH of a weak acid solution. So the first thing we want to do is you want to have a balanced equation. So here's our balanced equation. If they don't give you a balanced equation, you're going to have to write it out. So again, you have a monoprotic acid. It's going to react with water. It's going to give off its proton to water to form the hydronium ion, and then what's left over is your NO2 minus your nitrate ion, or nitrite ion, I should say. So it's all a 1-to-1 ratio here. So then you're going to set up your ice chart. So they're giving us 0.0200 molar solution of nitrous acid. So here we're going to put 0.200 for the concentration. We're going to ignore water because there's plenty of water, and it's really not, it doesn't really fit into the expression anyway, right? So remember from before with the equilibrium expressions, liquids and solids don't find their way into those expressions because they don't change in concentration. So we're going to ignore this. And then we have practically 0 to start with of your hydronium ion and 0 of your nitrite ion. So this is our initial conditions, our initial concentrations, what we start with, and then the change. And again, the change is going to be X. Since we have 0 product, it's obviously going to go in that direction, so we're going to lose reactant, so we'll have negative X. 1, because the coefficients are all 1. So we have negative X, we're going to lose a certain amount of our acid, and we're going to gain a certain amount, the same amount, in terms of your hydronium ion, and you're going to gain that same amount in terms of your nitrite ion. Okay, so we got our changes, and now we add these together to get the equilibrium expressions. So at equilibrium, then it's going to be 0.200 minus X for your nitrous acid, and it's going to be plus X and plus X for these two. Okay. So now we have our expressions at equilibrium of the amounts of our acid and hydronium ion and the negative ion. So now we write out the equilibrium expression, our Ka value, our Ka expression, the ionization of our acid. So Ka is going to be equal to, and it's going to be products over reactants, concentration of, so we have H3O plus concentration of that multiplied by the concentration of NO2 minus all over the concentration of the acid we have here, so concentration of HNO2. And all we need to do now is plug our expressions in. So here, again, we have X for the hydronium plus X for the nitrite. So those multiplied together is going to give us x squared over the concentration we started with here, which is 0.200 minus x. So 0.200 minus x. And again, here is where we can apply the x is too small approximation and see if it works. And it most likely will work. It's close. If we look at the, I should set this equal. If we look at the Ka value of nitrous acid, so the Ka value for nitrous acid is, where is it at? It's going to be 4.6 times 10 to the negative 4. So 4.6 times 10 to the negative 4. Now, in this case here, this is 0.2, right? So this would be 2.00 times 10 to the negative 1. And this is negative 4. So if you, that's a difference of 3 between negative 1 and negative 4. So it's probably going to pass the validity test, and we'll see. So here we'll do our x is too small approximation. So basically, again, what that means is we are going to assume that x is so small that even if you subtract x from 0.200, you pretty much still have 2.00. So we'll just make it 2.00, or I'm sorry, 0.200. All right, so then what you do is you solve for x. So you multiply both sides by 0.200, you square root both sides to get x, and then you get your answer. So if we do that, you get x, you get x is equal to, where is it? X is equal to 9.6. 9.6 times 10 to the negative 3. Okay, so now what we need to do is we need to validate our x is too small approximation using the 5% rule. So we're going to take this, divide it by 0.200. So if we take this divided by 0.200 multiplied by 100, if we take our calculator and calculate it out, we get 4.8%. So 4.8%, that's really close to the 5%. It's less than 5%, so it's valid, but barely valid. So so we can make that approximation. So good. So we got our x value. X, this is x. X is the same as our hydrogen concentration or hydronium ion concentration. So to find the pH, which is what we're asked for, we just take the negative log of the 9.6 times 10 to the negative 3. If you take that negative log, you get 2.02, a pH. pH is equal to 2.02. Let me double check to make sure I got that right. Yeah, 2.02 is the pH. So that's how you can use your ice chart. You can use the x is too small approximation and then show its validity using the 5% rule. And then once you do that, you know what the H plus concentration is, and then you take the negative log, and that's the pH. I hope this was helpful, and if you like this video, if you like my videos, please like, share, subscribe, hit the notification bell. Thanks for joining. I'll see you next time.